In Calculus 1 you have seen how to calculate various kinds of limits, and in particular undetermined kind of limits. But this only worked in particular cases, and now we want to see a more systematic way to deal with this kind of limits. So what I mean by undetermined limits are things like that. Let's say we look for the limit as x is approaching 1 of ln of x divided by x minus 1. The top ln of x approaches ln of 1, which is 0, and the bottom, x minus 1, approaches 0 as well. So we have an undetermined form of the type 0 over 0. In Calculus 1, you have seen how to lift this indetermination in various cases. For instance, if you have a quotient of two polynomials, the fact that they are both 0 for the same value of x means there is a common factor. So you can factor both top and bottom, cancel the common factor, and lift the indetermination that way. But in this case, for instance, with ln of x, there is nothing to factor, and what you've seen in Calc 1 would not apply. Similarly, if you consider this limit, when you plug x equals 0 at the top, you get 0 plus sine of 0, which is 0, and at the bottom 0. So you have again an undetermined form of the type 0 over 0, and again, factoring techniques or using conjugates or these kind of things do not apply here. Here is a case that you learned how to deal with in Calculus 1. When you plug x equals 0, you get root of 1, which is 1, minus 1, so 0 at the top, and 0 at the bottom. So again, undetermined form of the type 0 over 0. This one, you have seen how to deal with it. You can multiply top and bottom by the conjugate, in other words, root of 1 plus x plus 1. At the top you would get 1 plus x minus 1, so just x. At the bottom the conjugate times x. The x cancels out, and you end up with 1 over root of 1 plus x, which has, 1 over root of 1 plus x plus 1, which gives you 1/2 at 0. But we want to find a systematic way to deal with these three types of things. So we want to do away with the ad hoc techniques like using the conjugate or factoring or this type of things, and have something that also applies to situations where we didn't have a tool so far to calculate these limits. Another kind of indeterminate limit is when the top and the bottom go to infinity. For instance, here the limit when x is approaching infinity of x squared minus 1 over 2x squared minus 1. The top goes to infinity, the bottom goes to infinity. In that particular case, you've seen again in Calc 1 how to deal with this. The top and the bottom have the same degree, they are both polynomials. You've seen that in that case, the limit at infinity is a quotient of the leading coefficients, in that case 1 over 2. But formally, it's infinity over infinity, and so it can be decided easily in that case for two polynomials. But let's say for something like that, if you look at the limit of ln of x divided by x when x goes to infinity, top and bottom go to infinity, and now we don't have a general result for that. So this rule of de l'Hopital, which is the title of this section, is about giving a general principle to deal with all of these examples and more. So let's turn to the statement. The context is going to be to take two functions, which are going to be the top and the bottom in the undetermined limit, that are differentiable near a, except possibly at a. What that means is they're differentiable on an open interval centered at a, but possibly not at a. We want g prime of x to be non-zero near a, except possibly at a, and we're going to assume that we have an undetermined form of the type 0 over 0. In other words, the limit of f at a and the limit of g at a are both 0, or we have an undetermined form of the type infinity over infinity, so both limits at a are infinite. Then the conclusion is that we can evaluate this limit by observing that the limit, this undetermined limit f over g at a, is the same as the limit at a of f prime over g prime. And that's going to be the case whether the limit of f prime over g prime is a finite number or is infinite. So the first case, when both limits are 0, corresponds to the undetermined limits 0 over 0. The second one corresponds to undetermined limits infinity over infinity. Another remark about this result is that this a, where we consider the limits, could be infinite. We could have a version of the statement for a is positive infinity or for a is negative infinity, and we can have versions of this statement for one-sided limits. So replacing all instances of a with a plus or a minus. Now let's go back to the examples we've seen in the first slide. We've already observed that the assumption that the limit of the top and the bottom is the same and they're both 0 or both infinity are satisfied in each one of these cases. So we know that the conditions are satisfied because we're taking quotients of differentiable functions each time. So for the first case, if we apply the rule of de L'Hopital, what this says is that this limit at 1 of this quotient is the same as the limit at 1 of the quotient of the derivatives. And the derivative of ln of x is 1 over x, derivative of x minus 1 is 1, so we get the limit of 1 over x divided by 1, so just of 1 over x. And the limit at 1 of 1 over x is 1. In the second case, I have again a quotient of differentiable functions, undetermined 0 over 0. I can apply the rule of de L'Hopital, and it tells me that this limit is the same as the limit of the quotient of the derivatives of top and bottom. Derivative of the top in this case is 2 plus cosine x, the bottom is 1, and the limit at 0 of 2 plus cosine x is 2 plus cosine 0, which is 1, so we obtain 3. For the third one, again, we already have verified the assumptions for the rule of de L'Hopital, so applying it, we get that the limit is the same as the limit of the quotient of the derivatives. Derivative of root of 1 plus x minus 1 is just 1 over 2 root of 1 plus x. Derivative of x is 1, so we just get the limit at 0 of 1 over 2 root of x plus 1, which is 1/2. Then we had an example where the limit was undetermined of the form infinity over infinity. And in that case, we know what we should expect. We should obtain 1/2. If we apply the rule of de L'Hopital, we have the limit of the quotient of the derivatives. Derivative of the top is 2x, of the bottom is 4x. So we get in fact the limit of 2x over 4x, which is in fact the constant function 1/2. And so the limit is 1/2, as expected. In the case of ln of x over x, both go to infinity, so we can apply the rule of de L'Hopital. We obtain the limit of the derivative of ln of x, that's 1 over x, divided by derivative of x, which is 1. So we obtain the limit at infinity of 1 over x, which is 0. Now to prove the rule of de L'Hopital, we're going to need a generalized version of the mean value theorem that is often referred to as Cauchy mean value theorem. And for that result, we take two functions that are continuous on a closed interval and differentiable on the open interval, and we assume that the function g has a derivative that is non-zero on the open interval ab and doesn't take the same values at the endpoints. Then the conclusion is that there is some point between a and b where f prime of c divided by g prime of c is the quotient f of b minus f of a divided by g of b minus g of a. Now this is a generalized version of the usual mean value theorem, because the usual mean value theorem is a case where g of x is x. In that case, of course, g prime is not 0, we don't have the same value at the endpoints. And g prime of c is always 1, and g of b minus g of a is just b minus a. So what we get is that there is a c such that f prime of c is f of b minus f of a divided by b minus a. In other words, the average rate of change of f over the interval ab. So in Calculus 1 you have proved the regular mean value theorem, and because we're going to need that, I want to outline the proof for this Cauchy mean value theorem, and this is a very similar type of proof. Essentially you use an auxiliary function to which you apply Rolle's theorem, and the fact that the derivative is 0 somewhere gives you the needed condition. In that case, the function we're going to consider as an auxiliary function is h of x defined by f of x minus f of a minus this coefficient f of b minus f of a divided by g of b minus g of a, which should be the quotient of the derivatives that we are seeking, multiplied by g of x minus g of a. If you plug a in this function, you get f of a minus f of a at the beginning, and then g of a minus g of a multiplied by something else, so we get 0. Similarly, when we plug x equal b, we get f of b minus f of a, and then minus f of b minus f of a multiplied by g of b minus g of a divided by itself. So we end up with f of b minus f of a minus itself, so again 0. And the function h is defined as the function f, which is assumed to be continuous on the closed interval, differentiable on the open interval, minus a constant plus another constant times g of x minus g of a. So if both f and g are continuous on the closed interval and differentiable on the open interval, so is the function h. Therefore h has the same value at the endpoints as this continuity and differentiability condition, and therefore the theorem of Rolle applies to h on that interval to the effect that there is some c in the open interval ab where the derivative of h is 0. But if you look at the derivative of h, it's f prime minus g prime times this coefficient f of b minus f of a divided by g of b minus g of a. So when you look at what happens at c when h prime of c is 0, you get that f prime of c divided by g prime of c is the quantity that we are looking for, f of b minus f of a divided by g of b minus g of a. With this in mind, we can prove the rule of de L'Hopital, and we're going to just do the case where the limit of f is equal to the limit of g is equal to 0 and a is a finite number. The other cases could be taken care of in a similar fashion. Let's call L the limit of the quotient f prime over g prime, and we want to show that the limit of f over g is also L. We're going to introduce continuous extensions of f and g at a by defining capital F to be equal to f everywhere but at a, and at a we define capital F to be 0, and similarly for g, capital G coincides with G everywhere but at A, and at A is defined by 0. Because the limit of f and g at A are 0, what we are doing here is really taking an extension of f and g by continuity at A, so we get functions that are continuous at A. That means that if we take an x, for instance, greater than A, then this capital F and capital G are differentiable on the open interval ax and continuous on the closed interval ax. That's because everywhere but at A, they coincide with the function little f and little g that have the required conditions, and at A, which is the only place where we have potentially a problem for little f and little g, we fixed it. We get continuity of capital F and capital G. So that means that we can apply this Cauchy's version of the mean value theorem to capital F and capital G to the effect that there is some number c between a and x, such that capital F prime of c divided by capital G prime of c is capital F of x minus capital F of a divided by capital G of x minus capital G of a. By definition, capital F of a and capital G of a are both 0, so we obtain just capital F of x divided by capital G of x. One basic observation is that if x is approaching a, and of course here we made the assumption that x is greater than a, so x is approaching a from the right, then c, which is a number between a and x, which of course depends on x, is going to also approach a from the right. That means that if I look at the limit at a from the right of f of x over g of x, well, because little f and capital F coincide everywhere but at a, little g and capital G coincide everywhere but at a, I get the same limit. And according to what I have obtained by Cauchy's mean value theorem, this limit of capital F over capital G can be rewritten as a limit as c is approaching a plus of f prime of c divided by g prime of c, where c of course depends on x. But now capital F prime coincides with little f prime and capital G prime with little g prime, so we get the limit at a plus of f prime over g prime, which is L. This is for the limit from the right. Of course we can do exactly the same thing from the left and obtain the same result, and we can do use similar arguments for other cases for the rule of de L'Hopital. So now that we proved the rule of de L'Hopital, let's take a look at a few more examples. We're going to evaluate these various limits. So first, the limit as x is approaching 1 of x squared plus x minus 2 divided by ln of x. First thing we need to do is check the assumptions to apply the rule of de L'Hopital, and in particular we want to see if we indeed have an undetermined limit. So we plug x equal 1, at the top we get 2 minus 2, 0, at the bottom ln of 1, which is 0. So we have an undetermined form of the type 0 over 0, therefore the rule of de L'Hopital applies, and the limit should be the same as the limit of the quotient of the derivatives. So limit of 2x plus 1 for the derivative of the top, divided by 1 over x for the derivative of the bottom. At 1, if I plug 1 in this, I get 3 at the top, 1 at the bottom, so the limit is 3. For the second one, we are seeking the limit at 0 of e to the 3t minus 1 divided by t. If I plug t equals 0, e to the 0 is 1, so I get 0 at the top, and of course 0 at the bottom. So this is again an undetermined form of the type 0 over 0, and the rule of de L'Hopital applies to the effect that the limit of the quotient of the derivatives is the same. Derivative of the top here is 3e to the 3t, derivative of the bottom is 1. When I plug t equals 0 in this, I get just 3, and this is my limit. For the third limit, when x is approaching 0, if I plug that at the top, I get 0 plus tangent 0, which is 0. At the bottom, sine 0, which is 0. So I have again an undetermined form of the type 0 over 0, and therefore the rule of de L'Hopital applies, and I get the same limit as the quotient of the derivatives. Derivative of the top is 1 plus derivative of tangent, which I can write secant squared, divided by derivative of sine, that's cosine. I plug x equals 0 in this. At the top I have 1 plus secant squared of 0, that's 1 over cosine square of 0, and cosine of 0 is 1, so I get 1 plus 1. And at the bottom I have cosine 0, so just 1. So I get 2. This is my limit. Now I'm looking at the limit when x is approaching infinity of e to the x over x. When x goes to infinity, e to the x goes to infinity. So top and bottom go to infinity, and I have an undetermined form of the type infinity over infinity. That means I can apply the rule of de L'Hopital, get the same limit as the quotient of the derivatives. In this case, derivative of the top is just e to the x, derivative of the bottom is 1. So I get the limit at infinity of e to the x divided by 1. Since e to the x goes to infinity, this limit is infinite. Then we look at the limit when x is approaching 0 of x plus sine x divided by x plus cosine x. If I plug x equals 0, at the top I get 0 plus sine 0, so that is 0. At the bottom 0 plus cosine 0, and here you have to be careful, cosine 0 is 1. So that means we have 0 at the top, 1 at the bottom. The assumptions in the rule of de L'Hopital are not satisfied, and therefore we should not apply the rule of de L'Hopital. In fact, there is no need, because this is not undetermined limit. We have 0 at the top, 1 at the bottom. This is just 0, and this is my limit. Here you have to be careful to check that you are in a situation where you need to use the rule of de L'Hopital. Because if you go too fast and say, okay, well, this is in a list of things where I'm using the rule of de L'Hopital, and just apply it without checking, here is what you would obtain. The derivative of the top is 1 plus cosine x. The derivative of the bottom is 1 minus sine x. So if you look at the limit of the quotient of these two derivatives, you plug x equals 0 in this, at the top you get 1 plus cosine 0, that's 2. At the bottom, 1 minus sine 0, that's 1, so you would get 2. And 2 is not the limit of your original expression. We've seen that the limit is 0. So you see that you would get the wrong limit applying the rule of de L'Hopital in this context. And this is because the assumptions for the rule of de L'Hopital to apply are not fulfilled in that case. Finally, I want to point out that sometimes the application is a little less straightforward. So let's consider, for instance, a limit at infinity of x squared divided by e to the x. Both top and bottom go to infinity as x goes to infinity, so this is an undetermined form of the type infinity over infinity, and therefore the rule of de L'Hopital applies, meaning that the limit is the same as the limit of the quotient of the derivatives, so namely limit of 2x divided by e to the x. But we still have that the top goes to infinity and the bottom goes to infinity, so we have again an undetermined form. So it looks like we didn't gain anything here. However, in some sense we did gain something, because we don't have exactly the same limit, even if it's still undetermined. But it's still undetermined of a type for which we can apply the rule of de L'Hopital. So we can apply it again to that new function, to the effect that the limit is the same as the limit of the quotient of the derivatives. Derivative of the top this time is 2, derivative of the bottom is still e to the x, and now as x goes to infinity, e to the x goes to infinity, but 2 is constant, so this limit is 0. Let's do another one like that. Let's consider the limit at 0 of sine x minus x divided by x cubed. If we plug x equals 0 at the top, we get sine 0 minus 0, so we get 0, and at the bottom 0 cubed, so 0. So we have an undetermined form of the type 0 over 0. We can apply the rule of de L'Hopital. The derivative of the top is cosine x minus 1, derivative of the bottom 3x squared, and when we plug x equals 0 in the result, we get cosine 0, which is 1, minus 1, so 0 at the top, and again 0 at the bottom. So we get another undetermined form of the type 0 over 0. That means we can apply the rule of de L'Hopital to that new limit. And we get the limit at 0 of the quotient of the derivatives. Derivative of cosine x minus 1 is negative sine x, of 3x squared is 6x. If we plug x equals 0 in this, we get sine 0 at the top, so that is 0, and 6 times 0 at the bottom, so again 0. So this is again an undetermined form of the type 0 over 0. So we can apply the rule of de L'Hopital again. And we obtain again the quotient of the derivatives, limit of the quotient of the derivatives. So for the top, negative cosine x, for the bottom, just 6. And this time, when we plug x equals 0, we get cosine 0, which is 1, so we obtain negative 1/6 for the limit. And this is the limit of my original expression. Now turn to the next video to see other applications of the rule of de L'Hopital.